because we've already talked about the number of different protons in a molecule and we've talked about chemical shift, the next thing in line is integration. So the third thing that we have to consider when we're interpreting proton NMR spectrum is the area under the curve. And the area under the curve is the integration, and it gives us an idea of how many protons are responsible for that signal. And so if you look at the example shown here, there is this compound right here, which has 9 equivalent protons and 2 equivalent protons. And if you look at our spectrum, you see that there's a signal here at 1 that has an integration value of 7 and a peak here a little above 3, which is further downfield. And that's these 2 protons right here, the CH2 right next to the bromine. So they're de-shielded and shifted downfield. So this integration value is 1.6, but when we look at our molecule, we see we have 2 protons here, which would be for that signal, and 9 protons here, which would be for that signal. So the 1.6 to 7 ratio equates to 2 to 9. And so that integration line, that's the green line shown here, tells us the area under the peak. And it gives us information about how many protons, right? So that line is very helpful in us determining the area under the peaks. And if we look at this example, it gives a value here, the area under the peak, 27 to 40 to 28 to 42. So what happens when you get these kind of values is you take the lowest value and you divide each of these values by that number. And then that will give you some ratio. So this is 1. This would be 1.48, 1.05, 1.56, but obviously you can't have 1.48 protons or 1.05 protons. And so if you bring that to some whole number, it ends up being 2 to 2.96 to 2.1 to 3. Ultimately, what you get is 2 protons, 3 protons, 2 protons, and 3 protons. So now that we've determined those values, we could imagine the compound looking something like this. Furthest upfield would be this methyl group, 3 hydrogens right here, and then shifted downfield a little bit, we have the CH2 group, so there's those 2 hydrogens. And then even further downfield, right next to the oxygen, right, so it's de-shielded, the 2 hydrogens here would give a signal up here. And then this methyl group right here will give a signal at this point in the spectrum. So that just gives us a little bit of an idea of how we start with kind of very large numbers that we're not sure. We're gonna just bring it down to a value that we can actually use. Okay, another thing we have to think about is that symmetry can also affect our integrations. And so for the example of 3-pentanone shown here, we have 2 different types of protons. We have this CH2 and this CH2 that are equivalent. And then we have the 2 methyl groups at the end that are also equivalent. So the relative integrations should be 2 to 3. But in fact, it's 4 to 6. And so the actual ratio is 2 to 3. But once we're given the compound formula, we see that there's not 5 total protons in the compound, but instead there's 10, which would mean that there's symmetry. And so we can actually use the integration to help us determine symmetry as well. So if I ask, what would the ratio be in this compound? So how many different types of protons do we have? Here's 1 type, and here's 1 type. So there's 2 types. And the relative ratio between these 2 would be 1 to 3. Perfect. And now if we look at our second example, we have 1 type of proton that is a methyl group. So these 6 protons are equivalent. And then we have this additional type. So we also have 2 types of protons in this compound. And if we look at our relative ratio, we have 2 to 6. That would then become 1 to 3. 3 down, 1 to go. We're almost there.